Hello, and thank you for stopping by our poster. My name is Julie Younes. I'm a PhD candidate under the supervision of Professor Giovanni Grasselli at the University of Toronto in civil engineering with a geomechanics emphasis. Today, I would like to talk about salt rocks and its self-healing ability. So, to meet the emission reduction targets of the Paris Agreement and to decrease the dependency on fossil fuels, renewable energy sources such as wind and solar, although they are intermittent, they are becoming more and more essential every day. And with a growing global demand for energy, many countries are also focusing on energy security. Subsequently, this increases the importance of energy storage. Now, salt rock specifically, with its low porosity, low permeability, large size, compact structure, and frequent healing properties, is considered an ideal medium for energy storage. And currently, underground salt caverns are widely used for storing oil, gas, hydrogen, compressed air, and even nuclear waste. The operation of a salt cavern follows four distinct stages within its working cycle, including constant low pressure, injection, the constant high pressure, and the withdrawal phase. And since each energy storage medium requires a specific working period to meet the market demands, these cycles must be carefully studied. When a cavern is constructed in a rockfall formation, the surrounding salt undergoes changes, resulting in a narrow zone of damage known as the excavation damage zone. The deformation in this area can increase significantly due to the impact of pressure fluctuation during operation. Therefore, a competition arises between the increase in damage and the healing effect on the surrounding salt. To ensure the long-term stability of the cavern, it is crucial to study the self-healing behavior of damaged rock salt under short cycles. The nature of crack self-healing in salt involves three distinct physical mechanisms, namely the pressure closure, where the microcracks are closed under pressure and the two surfaces of the cracks will contact each other and form a chain network by bonding. And that way, the mechanical strength of the salt is restored. However, damage healing is affected by various conditions such as pressure, time, the initial damage of the sample, humidity, inclusions and impurities in salt, all of which can eventually improve or affect the mechanical and permeability properties of salt caverns. Thus, it is necessary to make a quantitative analysis on the recovery of salt. The salt rock samples selected for this experiment were taken from the Lochburg Formation in Canada. And since the salt is susceptible to weathering and damage from extraction and preparation, the samples were placed inside a healing chamber where they were subjected to a hydrostatic pressure of 10 MPa for 7 days. Before starting the healing procedure, ultrasonic velocity measurements were conducted and the samples were scanned via computed tomography or CT. Now, these measurements were repeated after healing as well. And to investigate the mechanical properties recovery, a digital image correlation system was adopted during the loading schemes. Damage was induced on one of the samples cyclically, and considering that the elastic stage has little influence on the damage, it was necessary to load the sample to the plastic stage. This damaged sample was once again scanned before and after being placed inside the healing chamber for a second round. And in that second round of loading, the sample was loaded until failure. Now, the second sample had a similar healing procedure, however, without undergoing any induced damage, so it was only subjected to one initial healing cycle. And to assess the internal damage from the CT scanning data, we first used the grayscale images. They were adjusted, corrected to reconstruct the 3D volume. And then to obtain the microstructural information, the voxels in the CT images were then classified to distinguish between the fractures and the salt matrix and to create the segmented volume. The structuring curve indicate that the compaction stage is insignificant in all the tested samples, and it was noticed that the actual peak strength gradually increased when comparing the undamaged and damaged sample. So, and also the elastic modulus on the sample healed twice was significantly higher than the undamaged sample, which was only healed once. So this suggests that only some parts of the internal microcracks are closed and healed in each cycle. Thus, the importance of understanding the effect of number of healing cycles on the damage. Also, the ultrasonic velocity measurements were used to assess and confirm healing, and it showed that the wave velocity of the rock increased rapidly after healing. It almost had a 6% increase. This phenomenon was further confirmed using the CT data. So we can definitely see a reduction of the initial damage value after healing. So in the first round, it decreased from 0.015 to 0.011, and the second round decreased from 0.018 to 0.016. Now, although we see a reduction of the damage in both rounds, the degree of recovery decreases the higher the initial damage, as well as the healing rate. And all of these results indicate the importance of healing cycles in a salt cavern. And with that, I would like to thank you for your attention. And if you have any question, please make sure to reach out.